Good morning.
Good morning.
Morning.
Morning to you. Okay, so we will continue from where we left last time. And just to remind you that we are looking at the transport layer and how it is supposed to support applications that are written by programmers. The last time we looked at the addressing, and we said when you write a program and you are trying to connect to another program on another machine, you have to give the address of the recipient, of the destination process. So I believe you remember that. So today we are turning our attention to connection establishment and connection termination. Most likely we will not finish both of them this session, but we'll see how far we go. Now, why are we looking even at connection establishment? Why are we really looking at this and we are really looking at what the transport layer does? Now, if you remember, we said the transport layer creates a connection, a transport connection between the processes that are communicating. Let me try and draw it. So assume that two programs are communicating. So that's program A or client communicating with a server. We said they create a connection between them, what is called a transport connection. But we said the transport connection is not a physical connection, it's a logical connection. But in any case, they create a connection and then they send data through this connection to each other, and then they terminate the connection. So the connection is a two-way connection. However, to actually send that data, and remember this is the application, they create a connection, and it is really the transport layer that creates that connection. So that's really a transport connection. In other words, it is the transport layer that creates that connection. But it is a logical connection, it is not physical. And it actually just exists on the two machines that are communicating. But we said that in the intermediate, we have these routers or network nodes that actually transport data to their destination. So data will flow from this machine and it will go to other intermediate machines before it gets to its destination. So assume that is the route that it follows and finally gets to its destination, this one. So it comes from this machine and uses the intermediate nodes to its destination. But now these intermediate nodes, they are really just running the IP layer. In other words, it is the IP layer that is really executing this transmission of the transport data. So when the transport layer wants to send data, it hands it over to the IP layer, so that now the IP layer can transport it as we have seen using the intermediate nodes. And then we said last time that the IP layer is unreliable. In other words, the transport layer is transporting data using a layer which is unreliable. And yet, the application expects the data to be delivered reliably. So now we are going to look at how does the transport layer use this unreliable layer to transmit data and still be able to establish a connection? How can it be sure that that connection has been established? Because remember, the connection is established between these two machines. these two. Yet the request to establish the connection must follow all these, must go through all these nodes. And if at some point the data can be lost, how will this machine A be sure that the connection request it sent arrived at B? And if B sends a reply and says, okay, I accept your connection, how will B know that the response was received? So that's really what we are trying to look at. How does the transport layer ensure that both sides are confident that the connection has been established? Because until the connection is established, we can't send data. But if in trying to establish the connection, we are never sure whether the connection has been established, because the request, either the request for connection or the response to that request is lost. You can't be sure it arrived. So how will you be sure that the connection has been established? So that's really what we are looking at, and how the transport layer ensures that that connection is established prior to sending data. Okay, so what we will do, we will first look at how do you establish a connection when the underlying network is reliable. So we'll first assume that this network here is reliable. We will make that assumption first, that it is reliable, so that we see how you can send it if it's reliable. And then we will look at the situation where it is unreliable, and how then we ensure that we are able to establish the connection. Okay, so with that background, let's just see what happens at the transport layer. So first of all, why do we establish a connection? What is the purpose of establishing a connection? The first one is it allows each user to know that the other end exists. We looked at establishing a connection for when we were looking at the wide area network, and we saw that when you're establishing a connection, you send a connection request from machine A to machine B, and then machine B responds and says it's willing to accept a connection, and that response goes back to A. So by the time that happens, they are both sure that the other one exists. And so now they can begin to send data. It's better than sending data when you don't know whether the other machine is even up and running and whether it is willing to accept the data. Now, establishing a connection also allows for exchange or negotiation of optimal parameters. In other words, they negotiate about certain things. For example, you can establish a connection and say, look, me, I'm establishing this connection and I want my data to be sent at 10 megabits per second. Now, if you don't say how fast you want your data to be sent, no one will bother to send it at the rate you want. It might be sent at a slower rate or a higher rate. It doesn't matter. It depends on what's happening in the network. So if there are more users, it will be sent at a slower rate. But if you want to be certain about, for example, the quality of service, then you have to establish that at the connection establishment phase. You have to say what you want. So notice that you can negotiate about the quality of service, even the maximum window size, the maximum segment size. So you can say, I'll be sending data and this will be my maximum segment size. And you negotiate with the other peer, so that by the time you start sending data, there's no confusion. What is your maximum segment size? Okay, so that's one of the things that connection establishment does. It allows you to negotiate the parameters that are important for that transmission ahead of time. And finally, it triggers the allocation of the transport entity resources. Now, obviously, this follows from the second point. You cannot say you want to send data 10 megabits per second, and then you don't reserve the capacity to do it. So whatever resources are needed to achieve your requirement will have to be set aside. So for example, you want to send data at 10 megabits per second. How much buffer space needs to be set aside for that? If you have specified your maximum segment size, you have said my data is going to come in at the rate of 10 megabits per second. How much buffer space do I need to keep? Those things will be worked out. So whatever resources are needed to make the connection work as required, those resources will be set aside. Usually it requires really just setting up some memory space for that communication. Okay, so we know why a connection needs to be established. It's an important thing so that there's agreement about how the data will be sent and both sides agree on it. So connection establishment is by mutual agreement, as we have seen. Both sides have to agree on how they are going to send data to each other. So we are going to look at two possibilities. One, how do you set up a connection when the network is reliable? Assume that the network never loses data. So that in this diagram here, once the transport layer sends the data, it will cross through the network to the other side and it will be received without anything getting lost or even damaged. So that is one case. The other case is when it's unreliable and there is no guarantee that anything will happen. And remember that unreliable is the default because IP by default is unreliable. But we'll take a view that maybe we have a reliable network and see how it works, and then try to see what would happen in an unreliable network. So in the presence of a reliable network service, we can accomplish connection establishment by what we call a two-way handshake protocol. Now, a two-way handshake protocol basically just means that this diagram best explains what a two-way handshake protocol is. That one side sent the request for connection. This is a request for connection to be established. So it sends, client sends a request for connection to the server, and the server responds with an acknowledgement or an accept connection request. Now, because we are assuming the network is reliable, we don't expect the request from the client to get lost. So when the client sends it, they are sure that request will arrive at the server. And when the server sends their response saying, I accept to connect to you, the server is also sure that the client has received that message. So basically, you just need two messages. And we call this the two-way handshake between the two senders. It's a two-way handshake. And it is sufficient in a reliable network. Now, so I'm going to explain how the two-way handshake protocol works, but first, you need to become familiar with these terms. I think we talked about the TS user last time. The TS user is the application that runs on top of the transport layer, and it uses the services of the transport layer. So it's called the transport service user. But then there is the transport entity, which is the entity that is active within the transport layer. So let's look at this diagram here. We are assuming that this is the transport layer. This is the transport layer. This is the application layer. And this is the network layer, right? So our TS user is this application. It's the one that's using the services of the transport layer. But within the transport layer, there's a transport entity. It is the one that communicates with the other peer on the other side. So the two peers, the two transport entities on both sides are the peers, and they're the ones that communicate using the transport layer protocol. So the transport entity, you have the transport entity on the sender side, and you have the transport entity on the receiver side. So the transport entity is basically that software or that agent that implements the transport layer protocol. So you have the sending transport entity and you have the receiving transport entity. So the sending side is the one that sends the segments, and the receiving side receives the segments. Now, I hope I have said it, but it's important for us to remember that the protocol data units sent at the transport layer, they are usually referred to as segments. Remember that at the data link layer, whatever is sent is referred to as a frame. At the network layer, whatever is sent is referred to as a packet. At the transport layer, whatever is sent is referred to as a segment. So if you're to use the correct term, those would be the terms you'd use. Segment at transport layer, packet at network layer, frame at data link layer. But the generic term is the protocol data unit. Every layer has a protocol data unit. So you can have the transport protocol data unit, the network protocol data unit, and the data link layer protocol data unit. So that's the generic term that came from the OSI model. So we will be sending segments at transport layer. But now there's a special segment you need to become familiar with, which is referred to as the SYN. The SYN is that segment which we said is used for creating a connection. So if you look at this two-way handshake, you realize there's that term referred to as SYN. It's a special protocol data unit which is used for setting up a connection. And we shall see how it is. In fact, let me just think I can explain it from here. Now, if you remember, we talked about the transport header. We looked at several things in the transport header. The first we looked at, of course, was the source port and the destination port. We said that these have to be put in the transport header when the segment is being sent. That was when we were talking about the address. Then we talked about the sequence number and the acknowledgement number, which by now you can see from this two-way handshake. There's a sequence number. This SYN is sent with a sequence number, which is chosen as X. And of course, the response is also sent with a sequence number, which is Y. So in any message that is sent, there'll usually be a sequence number. That's if you're using the reliable transport service. There'll always be a sequence number, and of course, there'll always be a response. But now I want to talk about the SYN. If you think about the earlier transport header we talked about, there were 6 flags. But now we have expanded these 6 flags, and these are the 6 flags. There's urgent and acknowledgement and all those others. Now notice that there's one here called SYN. So when you are sending the request for connection, this SYN bit, they are just bits, there are 6 bits. So when you're sending the request for connection, this SYN bit must be set to 1. And that's why the packet is also referred to as an SYN packet. So that means that this bit SYN is actually set. When it is not set, of course, it is 0. But when it is set, it is 1. Okay, so that's about the segment. And there are other segments that are set. We shall look at them later. Remember that there are these 6 bits, the reset request. So if you are resetting the connection, you would set that reset, RST bit. If you are acknowledging, you would set the acknowledgement bit, and so on. We will look at them as we go on. When they come up, I will remind you. There's also, notice there's the FIN. After SYN, there's one called FIN, and that is for terminating the connection. So when you're terminating the connection, you would set the FIN bit. When you're creating the connection, you set up the SYN bit. Okay, so that's as much as far as the segments are concerned. And then the other thing you need to become familiar with are connection states. A connection, even though we say it is established, it goes through various stages until finally it comes to what we call the established state. So a connection may be in different states at different times. So we shall look at the different states when the appropriate time comes. But notice that there's a listen state, there's an open state, and there's established state. And there are many other states anyway. So those are important things to remember as we talk about what we wanted to talk about, which is the two-way handshake. And the two-way handshake is a protocol that's only used when the network is reliable. Now, this diagram here is more important when we start programming, but I'll just introduce it at this stage. I talked to you about last time about the connect primitive or command that you put in your program when you want to create a connection. And then I explained to you that the server is usually up and running by the time the client creates a connection. The server is usually up and running. And I said that the server is usually up and running 24/7. However, the client program is not always running. It depends on when the user wants to connect to a server. That's when they start up their client program. But the server is always up and running, ready to receive any request from any client. And then we say that the state in which the server usually is called the listen state. The server is usually up and running and is always ready and willing to listen to all connections that are coming in. So this diagram is trying to explain that. Notice that this is the server side, this is the client side. So by the time the client decides to connect to the server has already done several things. The server has already created a socket, and a socket, remember we said, was the port. Remember we said that that combination, that composite address we were talking about, it can also be referred to as a socket. So by the time the server is receiving a request from the client, it has already created the socket. It has already provided the address or the port number on which it is going to listen. So if it's a web server, it has already said, look, I'm going to listen at port number 80. So it has already created the socket without providing the address. So this just creates the data structures we talked about. There are some data structures that have to be created, and then you bind an address to it. Now, after you bind that address, the server then listens or issues a listen command, which basically says how many requests it is ready to receive or can be waiting in its queue at any one time. And then it issues an accept command, which basically means I am ready to receive any request. I've already specified I've already created a socket, I've already specified what my address is, and I've already specified how many requests I can listen to at any one time, and now I am waiting. So by the time that command accept is issued, the server is waiting. And that accept command is a blocking command, which means it will be blocked until a request comes in. So on the server side, it will just be sitting there waiting. Now, the client, of course, when it is ready to communicate with the server, it will create a socket. And remember, we said that the client doesn't normally give itself an address. The operating system will give it an appropriate port number, because usually there are many programs that are running on that machine, and the operating system will give each one of them that wants to communicate a port number. So to avoid a client choosing a port number that's already there, you can as well just let the operating system give you a port number. So the client usually doesn't specify its own port number, but when it's connecting, remember we said it must issue an address of the recipient. So it will say, I want to connect to the server on such and such a machine with such and such an address. So at the point when it connects, remember that a message will go from the client side to the server side requesting to connect to the server, and the server will respond back to the client and say, look, I am willing to connect to you. Now, if it's a reliable connection, it will be a two-way handshake, even though in this diagram it's written three-way handshake. But if it is a reliable network as the one we are currently discussing, it will be a two-way handshake. One message from client to server, another message back from server to client. When it is an unreliable network, which is what we are interested in, it will be a three-way handshake, and we'll talk about that as we go. So really, what we are looking at is what happens at this point. When the client decides to connect to the server, what really happens? So if it's a reliable network, it will be a two-way handshake. So how does a two-way handshake work? So a connection is opened when a user, that's an application, the TS user is the application, issues a connect command, as we have seen. So it will execute that command, and this will trigger the transport entity. Remember, the application is running on top of the transport, so it will trigger the transport entity to send an SYN message or protocol data unit. Now, the SYN will just carry a sequence number, and that sequence number has a purpose. So if I go back to this diagram here, after the client executes a connect command, then as we said, it will trigger the transport layer to send this SYN message. And the SYN message must contain a sequence number. Why must it contain a sequence number? Basically, the sequence number is telling the recipient. So this message is telling the recipient the two things. It says, I am requesting to connect to you. That's number one. That's the SYN part. The sequence number tells the recipient that the sender will start sending messages starting with sequence number X. In other words, once the connection is established, my first message will start with sequence number X. Of course, the server will also have to say, I am willing to connect to you, and my messages will start with sequence number Y. So the SYN always has a sequence number which says the starting sequence number for the messages. So if, for example, the sequence there is 10, then the client is saying, I want to connect to you and my first message will be sequence number 10. So once this connection is established, the first message sent by the client will have sequence number 10. The second message will be sequence number 11. The third will be sequence number 12, and so on. So X is the starting point. So we talked about agreement. They have to agree on that before they start sending messages. So bullet number 3, we have looked at the first two. So this segment, that is the SYN segment, will be carried to the receiving transport entity. And remember, the receiving transport entity is already in the listen state. It's already waiting. So the server is already waiting. And that request will be interpreted as a request for connection. So you're still talking about the first request being sent, the SYN. It is sent and it is received by the server that is waiting, and the server interprets it as a request for connection. Now, the receiving transport entity, which in this case is the server, signals to the user. Remember, this message is received by the transport layer, but there's an application running on top of the transport layer. So the transport layer here, we are saying, signals to the application that a connection is being required. In other words, a connection is being opened so that the application is aware. And then the transport layer sends a connection accepted message. It sends back a connection accepted message, which is also an SYN. In other words, that message will have that SYN bit also set, but it will be understood to be a response to the request message. So it sends that as a confirmation to the remote transport entity, in other words, the transport entity that initially sent that message. And then notice that the connection moves to the established state. The connection moves to the established state. And also notice that the confirmation SYN carries a synchronizing sequence number. I have already explained that when the server is responding, it also must say the sequence number it will use to begin the sending of messages. So it also gives its own sequence number. Now, let me mention about this established state. Now, this is the state diagram for connection creation, establishment, and termination. Now, initially, the connection is in the closed state. In other words, there is no connection. But when the SYN is sent, notice that this is active open. When the first SYN was sent from the client moved into a state called the SYN sent state. And now it is waiting for a response. On the other side, the server is already in the listen state. It's already in the listen state, waiting. And when it receives the SYN from the client, as we said, it now goes into the established state. After sending, remember, after sending an SYN, it goes into the established state, which means on the server side, the connection is already open. When the client receives the SYN from the server, it also moves from the SYN state to the established state, which means the connection is now open. So when they both move to the established state, it means the connection has been created, it is open and ready to be used. So what we are saying here that on the server side, after it sends the connection accepted request, it moves to the established state. And the SYN is sent back to the client carries a synchronizing sequence number. When the corresponding accepted request arrives at the initiating entity, which is the client in this case, then the application or the TS user is informed. It is informed that a connection has been established. First of all, remember that it is the client that executed the connect command. It was the client application that executed the connect command. So when this SYN comes back to the client station, the transport layer then informs the application that the connection you requested has now been established because you have received a response from the server. And then the connection is moved to the established state. So that basically is the two-way handshake protocol. And the purpose of the two-way handshake protocol is to create a connection that can be used for communication. Any question on that process, the two-way handshake protocol? Yes.
I have
Craig,
a question. Yes, if
you have a question?
yes, if two client processes are establishing a connection at the same time and their port numbers are really close. Let's say
The
like
what?
their port numbers are really
Mm.
close, like 1000 and 1001.
Mm-hmm.
And see, this is going to be the start of the numbers as they generate sequences. So
Mm-hmm.
how, see, let's say this 1000, it will when it generates 10 messages, it will move 1000 to 1010, and this one for 1001, it will move to 1011. So we
Mm-hmm.
can see there are two messages that will have similar sequential numbers, like 1005. The number 1005 can be found for messages from client A and client B. So how are those two client messages from those different clients separated, even though they have similar sequence numbers?
Okay. Thank you for that question. I understand what you're saying, but it makes me want to ask a question first before I respond to you. I want to believe that we did what we call what? Reliable data delivery at the data link layer when we were talking about the stop and wait protocol, the, what is it called? Go back N and so on. Did we do that with this class?
Yes.
We did it. Correct? Did we do go back N? Did we do stop and wait?
In earlier networking. Yes.
Pardon?
Yes, we did.
In second year, right? Yeah, so this is very close to that. Remember that the go back N and the selective
Yes, we
print.
did.
Yeah,
Yes,
so
earlier.
you need to remember that as we do this, because remember that this is also a sliding window protocol. Eventually, when we get to it, we will realize that it's a sliding window protocol, even though right now we are still dealing with the connection establishment. But when we start sending data, we will use the sliding window protocol. So if two entities are communicating, okay, I'll try to draw it here. I hope I can draw it here. If I can't, I'll have to get what we call the blackboard. So we assume that these two sides, they are communicating, right? In fact, the difference in the number, it doesn't even matter. They could all start at 0. So client may send a request with SYN sequence number 0. Say I will start at 0. And the sender could also say, look, I am also sending you my sequence number, it is 0. The numbers actually don't bring any confusion at all. Because remember that for the sliding window, the sender has a window of sequence numbers that it's currently waiting on. So it will have, for example, I am able to send data from 0 to 7. In other words, I'm allowed to send from 0 to 7 without waiting. Okay? Which means it will have sent requests from 0 to 7 to the server. And now it is waiting for a response. So when a message comes, and remember the messages are going in different directions. So when the server sends the reply, the client will look at the sequence number. So if 0 comes back, it will then get rid of 0 and slide the window. When 1 comes back, it will slide the window and so on until maybe it has received acknowledgement for all of them. So it will slide the window to 8 to maybe 15, something like that. So it is using the sliding window to keep track of the acknowledgements that are coming from the server. Similarly, the server is also waiting for messages from the client. And so it knows that it can start remember the client had already said, my messages will start from 0. So it's also waiting for messages from the client, and maybe they have agreed on a window size of 7 or 8. So it's also waiting for messages from the client from 0 to 7. So when the first message 0 comes, it will accept and acknowledge and slide the window. And when the second one, number 1, comes, it will acknowledge and slide the window and so on and so forth. So there will be no confusion because these messages are traveling in different directions. And the buffers have already been set aside because remember we said that one of the things that happens during establishment phase is to negotiate the parameters and also to allocate the buffer space and all the entries in the connections table. So there'll be tables, there'll be buffers and everything set aside ready for the data to be sent. So please remember that the sequence number is for the data transfer phase. This is just getting ready for the data transfer phase. So once the connection is established, then data will be transferred. And the first data that will be sent will be based on the sequence number that was established during the connection establishment phase. So there will be no confusion. Even if it was the numbers you've given me, 1,000, it was starting from 1,000, and the other one was saying it's starting at 1,001. There will be no confusion whatsoever. Because in that particular case, what will happen is that the client has already said it will start from 1,000. So this 0 here will be 1,000. This 0 here will be 1,000 to 1,008 or 7. This one, the send window, remember there's a send window and the receive window. So maybe I'm confusing you because I'm not writing both. There's a send window and a receive window on both sides. So let's not forget that. But the send window on the client side will start from 1,000 to 1,001. And the receive window for the server will now also start from 1,000 to 1,008 because already the client said that I will start from 1,000. So the receive window will start from 1,000. Now on the other side, the server had said, I'm going to start from 1,001. So the send window on this side will start from 1001. So this one will start from 1001 to 1009 or something like that. And the receive window on this on the client side will start from 1001 and will go on to whatever the window size is. So there'll really be no confusion. If you remember those protocols that we did, then you will understand what's going on here. I hope that answers your question.
Yes, it has.
Right, any other question? Okay. So this is just a diagram to show what happens. As we said, remember that we are using the two-way handshake protocol. And here, this is the server, which is already in the listen state. So notice that initially the state was closed. It went through all those things until now it is in the listen state. And it's in the listen state that now it receives a request for connection, and then it sends back an SYN and goes into established state. Meanwhile, on the client side, it moved from the closed state, and when it received the SYN, it went into the SYN state, and then later on, when it received a response, it went into the established state. So this is the normal case. This is not the normal case. In other words, establishing a connection where the other side is not in the listen state is very difficult, because the question is, how do you agree on when to start sending the SYN? When does the agreement take place that now let us create a connection so that I send you my SYN and you also send me your SYN? How will that happen? And how will you be sure that the connection has been established anyway? At what point? Because these requests are sent, there is no criteria that will enable them to start at the same time as shown in this diagram. So perhaps one will start sending the SYN at a very late stage, and one will send its SYN early. It's very difficult for them to synchronize. It's very difficult for them to synchronize when you are having this, both sides initiating the connection. It's always better when the other side is already waiting and listening, and then you connect to it at that point. But this second one is very difficult to establish, but I guess it could work. Okay, so we have established that when the network is reliable, a two-way handshake will work. It will just work as we have said. Now, assume the network is unreliable, and even let's not assume, the internet is unreliable. So try to establish a connection on the internet, and the internet is unreliable. What would happen if we use the two-way handshake? Could we really establish a connection? It is possible to establish a connection, but there is no guarantee that the connection will be established, because the first SYN that is sent, there is no guarantee that it will arrive. And remember, the network layer, because it's unreliable, it doesn't acknowledge. So when the first SYN is sent, it will never be acknowledged, because that's not how a connectionless network behaves. It doesn't behave that way. And when the response is sent back, the other side will also not acknowledge. And so you don't know whether it arrived or it didn't arrive. But in the case where they both arrive, then obviously the connection will be established. So we are going to look at some of the things that could possibly go wrong in the establishment of a connection that will hinder the connection being established. We are going to look at those things that could make it difficult for a connection to be established. Now, in a nutshell, we can have duplicate and obsolete SYN segments. Because right now we've only talked about SYN. We could have a duplicate or obsolete SYN segments. But when we go into the data transfer phase, we could also have duplicate and obsolete data segments, because it will be the same thing. The data segment will be sent, that with the first sequence number will be sent, and it may or it may not arrive. So ultimately, you'll end up with duplicate or obsolete SYN or data segments. And this arises from messages that are lost or delayed. Now, let me explain what I'm trying to say. If one site sends an SYN to the other side, it could be SYN or data, doesn't matter. When it sends a message, that message could get lost. So that's the first scenario. It can get lost. Okay? The other thing that could happen, it can get delayed. Remember that on the internet, data they take different routes. And so there is no guarantee the order in which they will arrive. But secondly, they could get delayed because at every intermediate node, there is a queue. When data comes into a router, it goes into a queue, and then it makes its way to the head of the queue. That's when it is transmitted to the next node. When it gets to the next node, it goes to the bottom of the queue, and then it makes its way up to the head, and then it is transmitted, and so on. So at every stage, there's a queue. At every intermediate node, there's a queue. And that causes delay. So at every node, the message has to wait for a certain time before it is transmitted. Now, when the network is very busy, it means all those queues are most likely full. So it will take a long time for the message to reach its destination. And it may reach its destination when already the sender has given up and has decided to retransmit. So the retransmission may arrive before the earlier one, which is still making its way through the queues to the destination. So once that retransmission is done, we really have duplicates. And if the second one arrives before the first one, then this first one will now be said to be obsolete because it has arrived when it is not required. So let me explain what that means. Assume that the sender was trying to send an SYN to this site, and it is waiting for that acceptance message to come back, and it is not coming back. So a retransmission is done a retransmission of that SYN is done. And so now we have two SYNs in the system because a retransmission was done. Remember, SYN is sent by the transport layer. So the first SYN was sent, but it has delayed in the network because the network is busy. And so the transport layer has decided to retransmit the SYN because it has waited for that acceptance to come and it didn't see it. So it has retransmitted. So this is the second SYN. Now this SYN arrives before the first one. So eventually when this one arrives, it will be obsolete. It's really not required. So it's coming in, but it's really obsolete. And that could happen even with data. Data has been sent, and now the data has not been acknowledged, so it has been retransmitted. And once it is retransmitted, maybe the retransmission arrives before the first one. So the first one, when it finally arrives, it will be obsolete. Or it will be said to be a delayed SYN or a delayed data segment. And the issue here will be, what do you do with that obsolete? How do you even know it's obsolete? Because if it's coming in and saying, look, I want to establish a connection with you, how do you know that it's not a new one? How do you detect that it's a duplicate? So that's really what we want to find out. How do you detect it? And can you even detect that it's a duplicate? So we have this problem of duplicate and obsolete messages that come in either because the message got lost and a retransmission was done, or the message was so delayed in the network and a retransmission was done. So now we have duplicates and one of them is obsolete. And if you're not careful, you may use the obsolete to create another connection when it is really not meant to create another connection. Okay, so we look at those problems, and I think I've explained here. Because of a lost message, I've used this slide to explain that a message may get lost, and then a retransmission is done, and then therefore, then you end up getting a duplicate. Or a message may be delayed, and an SOI may be delayed, and then you do a retransmission, and then it becomes obsolete. And the same for data. Data may be delayed, it may be lost, and when a retransmission is done, either it will be seen as a duplicate or as an obsolete, depending on when it arrives. So that's the issue we are dealing with. If the network is unreliable, can the two-way handshake still work? And the answer will be that it can't work. And now we will need what we call the three-way handshake. So let us look at some of the problems that can happen with those duplicates and obsolete. One, they're listed here and we shall go through them one by one. So a duplicate SYN arrives after the connection is established. What do you mean by after the connection is established? Remember that there are now two SYNs. The first one was sent, it got lost or it got delayed, and now we had a second SYN. So the second SYN was used to establish the connection because it arrived first. So it established the connection. Now the duplicate or the obsolete one arrives after the connection has been established. And what do you do with that? Now, the second situation is where a connection was established using the second SYN, the one that was retransmitted. It established a connection. The connection was used to transfer data, and the connection was closed. And then the obsolete SYN arrives after the connection has been established, data has been transferred, and the connection has been closed. That's when the obsolete message is arriving, after the connection has been closed. The third situation, the C, is about data. Duplicate data arrives after the sequence number has wrapped around. And this, I need to explain about the sequence number wrapping around. And this has to do with the window size. Because let's assume you have 3 bits. Assume you have 3 bits for the sequence number. So you can have sequence number 000, 001, 010, and so on. Basically, you can have from 0 to 7. And if you are using 3 bits, it means that when you reach number 7, you have to wrap around. The sequence numbers have to wrap around to start from 0 again. Because you only have 3 bits. And with 3 bits, you can only represent 3 numbers, three bits, that is. So you can have from 000 to 111. So if you use 00 to number your first data item, the second one is 001, and so on until the 7th, or is it the 8th? The 8th data item will be numbered 111. The 9th data item, what number will you give it? And you only have 3 bits. What number will you give it? You'll have to wrap around back to 0, 0, 0. So the 9th data item will be number 0, 0, 0. The 10th will be 0, 0, 1. And so up to data item, the 16th data item, which will again have 1, 1, 1. And now the 17th data item, what number will you give it? You'll have to wrap around again back to 0, 0, 1, 0, 0, 0. So coming back to problem number C. A duplicate data arrives after the sequence number has wrapped around. So let's assume that the second data item, which was 001, was sent. And then all the others were sent up to 111. From 0 to 8, they were all sent. Now, 001 got lost, or let's assume it got delayed. And because the 001 got delayed, a duplicate was sent. The duplicate 001 was sent and it arrived. And now we have wrapped around, we are sending the 9th data item. And before the 001 of that new sequence numbers for number 9 to 15, is it 9 to what? No, actually 8 to 15. Before that 001, for the second set of numbers, the other 001 from the previous arrives. How will you know whether you're dealing with the 001 of this first set or the 001 of the second set? How will you distinguish them? And they are all carrying the sequence number. That's another problem. And a duplicate can also arrive after the connection has been closed and a new one established. In other words, there was a 001 sent when a connection was opened. And because it did not arrive, a duplicate was sent. And the duplicate arrived. Now, the one that got delayed arrives after the connection has been established, utilized, and closed. So it arrives in a totally different connection. What do you do? What do you do? So those are the problems that you have to deal with, and you realize that the answers are not that easy. So I hope I've explained the issue of wraparound. That's important. The issue of a connection has been established and already closed. Those are important things. So I'm going to show you through a diagram. Of course, you can read. This one explains it, but a diagram would explain it better. So in this particular case, we're talking about a duplicate SYN arrives after the connection is established. So if you look at this diagram, you notice that the first SYN has a sequence number of X. So it arrived, and notice that the server accepted it and sent an accept request. So it accepted that connection, and it also sent an acknowledgement with its own sequence number. But if you look at the client side, the client actually waited for this SYN to come back and gave up. It timed out, and it sent a second SYN. Notice that the sequence number for the second SYN is different, because this sequence number is basically just a random number. So even if you say that you will send a duplicate, the likelihood of you choosing the same sequence number is very difficult because it's a random number. So it timed out and sent a second SYN with a sequence number Z. Now notice that the SYN was sent before the acknowledgement arrived. So it timed out and sent an SYN before that acknowledgement arrived. But immediately it sends it, an acknowledgement arrives. So it really doesn't know. Maybe it just assumes that the SYN has arrived very quickly on the other side and a response has been received. So the question is that acknowledgement, as far as the client is concerned, is it acknowledging the first SYN or is it acknowledging the second one? Now, as far as the client is concerned, it is acknowledging the second SYN because it doesn't know. It already timed out, and so according to it, it is acknowledging the second SYN. And so it assumes that a connection has been established. So we enter the data transfer phase. Now, notice when the client sends the data, the first data will have sequence number Z. As far as the client is concerned, it will send data with sequence number Z. When that data arrives on the server side, the server's window, as we said, receive window is expecting sequence number X. Because when it acknowledged knowing that the client will send data starting from sequence number X. But the data that now arrives is sequence number Z. And the question is, will communication take place? So it will send Z, Z plus 1, Z plus 2, Z plus 3. Do you think communication will take place? And this is a question to the class. Do you think communication will take place? Yes? Mikuri Adrian. Did I see your hand up?
I don't think communication will take place.
Why?
Or because the server is waiting for a while while receiving other packets.
Mm. So when the first data item from client with sequence number Z arrives at the server, what did the server do?
I think the server would still be waiting for a while in this case.
So what will it do with this Z that has arrived?
Receive and discard.
Yeah, exactly. It will discard it. Unless it falls within the receive window. Unless it falls within the receive window. But if it's far away from the receive window, it will be discarded. Then Z plus 1 arrives, it will be discarded. Z plus 2 arrives, it will be discarded. So no communication is taking place. And why is it not taking place? Because of these delays. The unreliability of the network is hindering communication from taking place. And with the two-way handshake, we have no way of knowing. The client has no way of knowing that this acknowledgement is the acknowledgement of the previous one. Because the acknowledgement only carries the sequence number for the server. So the client has no way of knowing that it's the one it had sent which had Y is being acknowledged, or is it the Z that's being acknowledged? It doesn't know the difference. Okay, so that's the first problem. So already with that, you can see that the two-way handshake is not sufficient to establish a connection in an unreliable network. So that's the first problem. The second one is the duplicate SYN arrives after the connection is established and closed. So again, we look at a diagram. You can look at the explanation later, but this is the diagram. So the SYN arrives after the connection has been closed. If you follow this diagram, you notice that the connection was closed. That dotted line is the point at which the earlier connection was closed. So the assumption here is that Within that connection, there was an SYN that was sent to establish that connection. Either it got lost or delayed, and a second SYN was sent. And that second SYN established the connection. Communication took place through that connection, and finally the connection was closed. While this first SYN was still making its way through the network. And as I've explained, when the network is busy or the route that it follows is very busy, it can take a long time because at every intermediate node, it has to make its way to the beginning of the queue, the front of the queue for it to be transmitted to the next node. So this is a possibility. It may sound like it is rare, but it can happen. So the SYN arrives after the connection has been closed. It arrives at the same machine, and the receiving application or the transport entity obviously assumes that this is a new connection request. But it is obsolete. It's really obsolete. So it arrives and notice that B responds because B doesn't know. It just sees a connection request coming in and assumes it's a new connection request. So it responds with SYNJ. But now the computer A on which the other application is executing actually sends an SYN for a new connection. It sends an SYN for a new connection, and the sequence number is K. So K arrives, but it arrives after the obsolete SYN arrived and a connection was established. Now, B does not know the difference. So it discards this SYNK. It assumes SYNK is a duplicate because after all, it has established a connection, so it drops it. Now notice that when A begins to send data, it starts at at K. So it sends K plus 1. Now what is B waiting for? B is waiting for I plus 1. So when K plus 1 arrives, it's discarded. K plus 2 arrives, it's discarded because it's waiting for A to start at I. So again, communication does not take place here because of this obsolete SYN that arrives at a much later time than it was expected to arrive, and it brings confusion and causes communication not to take place. So that is problem number 2. So we are just really highlighting problems that can occur when you're already working in an unreliable network. If it's a reliable network, no issues. Everything will work correctly. But when you're using the two-way protocol, where two-way just means you send an SYN and the other one sends you back an SYN with its own sequence number. Now, if we continue that in an unreliable network, it doesn't happen. Okay, so that's the second problem. The third one is that a duplicate data arrives after the sequence number has wrapped around. So here we have another diagram. Again, you can read the explanation there. So if you look at this diagram, notice that the transport entity is sending data. It started actually from sequence number 1. And it sends sequence number 1, 2, and now we have an arrow there showing sequence number 201. So it sent from 1 all the way to 201. Then it sent from 201 to 401. And then from 401, I'm sure it reached some number and then it wrapped around. And it sent again sequence number 1. And then it went to 201, and then to 601, to 801, to 101, and so on and so forth. And then it wrapped around. And then it started at sequence number 1. Now, So that means that this sequence number one, the first one that is crossing downwards, the blue line that's crossing downwards, notice that the sequence number has wrapped around twice before it has actually arrived at its destination. The sequence numbers have wrapped around, I believe, twice, because I can see sequence number one again, and I can see another sequence number one further down. So it arrives at that time, and it is obsolete. And here we are talking about data. So if it was a file, that means that sequence number one was carrying the earlier part of the file. It was carrying data from the earlier part of the file, maybe the beginning of the file. And now where we are at further down the file. So anyway, it arrives, and because the receiver doesn't know, it just accepts it. It accepts it. And notice the sequence number one that has also been sent, which is the one that's supposed to be received, arrives after the obsolete one has already arrived and been accepted. So it will be seen as a duplicate. The two sequence number ones arrive at almost the same time, one a little bit earlier. The sequence number will be seen to be a duplicate, and so it will just be discarded. So if you are transmitting data, it means you already have a mix-up in your data. You already have a mix-up in your data. And that's not a good thing. You have received data, but it's not the correct data, or it's not in the correct sequence. I hope you see the problem there. That an obsolete data segment arrives, and because it's not possible to detect that it's a duplicate, that the duplicate had been received, or maybe it was, it's something that was sent much earlier, you're not able to detect that, then you actually accept it and you mix up the data, so the receiver receives incorrect data. So that's another problem that can arrive. And finally, the last one here is that the duplicate data arrives after the connection was established, utilized, and closed. So this duplicate wants to arrive in a new connection. So it's slightly different from this one. This one arrives within the same connection, only that the connection is wrapping around. The connection is wrapping around, but it is still within the same connection. Now, in the second one, you are arriving in a different connection. So if you look at this diagram, notice the dotted line is where the connection was closed. So above the dotted line, notice that an SYN was sent, a second SYN was sent to establish the connection, and then we started sending the data sequence number one. And so sequence number one was sent, all the way to sequence number 201 was sent, all the way to 401 was sent, but that 401 has taken a very long time. And in the end, the connection was closed. So whatever was sent after 401, we assume that they arrived, but this 401 somehow got lost or got delayed in the network. And so it's arriving much, much later after a second connection has been established and data is already being sent. So this SN401 is really not meant to be in this connection. Maybe the connections are being used for totally different things. But anyway, it arrives during the second connection. And it arrives just before the correct SN401 for that connection is received. And because the receiver doesn't know how to detect these anomalies, it accepts the obsolete and gets rid of gets rid of that correct one. And once again, we have problems with communication. We have received the wrong data and we didn't know it. So those are possible problems. And maybe we need to stop. What time are we stopping? What time does this class end? It's at 10:45, right?
Yes.
So we have 10 more minutes. Okay, so I believe you have understood those problems. Any one of them that you don't understand? Any one of those problems that is not clear? Okay, so really what we are really saying is this, that with a two-way handshake, you are not able to detect certain anomalies. You are not able to detect certain anomalies. So what is the solution to this problem? And the solution to this problem is basically something we call a three-way handshake. Now, in order to solve this problem, certain decisions had to be made. One, how to detect duplicates. So one of the things is to be able to detect duplicates using sequence numbers. And that will become clear when we look at the three-way handshake. In the three-way handshake, the acknowledgement of the sequence number includes two sequence numbers. So for example, if the client sends an SYN and say, my sequence number is I, the server will respond and say, look, the sequence number is J, but I'm also acknowledging your sequence number I. So the server will say, my sequence number is J, acknowledging the original sequence number I. So now when the receiver receives J and I, they will be sure that the sequence number which is being acknowledged is I. And so they can tell whether there is a problem with the connection establishment. So we are using duplicates to solve the problem of duplicates. We are using sequence numbers to solve the question of duplicates so that it's easy to know whether something is correct or it is not correct. And then the other thing we are doing, for example, this SYN that arrives after connection has been closed. You need to know whether it is the SYN for a previous connection or whether it's an SYN for a new connection. And in order to do that, in order to solve that problem, this three-way handshake was developed as a means of solving that problem. And with three-way handshake, it means that the client sends the request for connection to the server. The server responds in the way I've already explained, acknowledging both their sequence number and the sequence number of the originator. And then the originator sends back an acknowledgement to the server. And it is those three requests, those three SYNs that will establish the connection. So the connection is established with three SYNs, one from the client to the server, one from the server to the client, and the client sends a third SYN back to the server, so that it's easy to know whether an SYN is from a previous connection or another connection. So in a nutshell, that's something that will happen in the three-way handshake. And lastly, the sequence number for any connection starts from a number far removed far removed from the initial sequence number. So for example, let me come back to here, this problem here. Now, if you look at this, this diagram, you notice that some data with sequence number 401 arrives in a new connection, which basically assumes that the second connection also started at sequence number 1. It started at sequence number 1, and the previous connection started at sequence number 1. And that's why this 401 can be accepted within the second connection, because they both started at almost the same sequence number. So now the solution is to say this: once you have created a connection and you started at sequence number 1, maybe you ended at sequence maybe 900, the second connection you create should not start at 1 as well. It should start maybe from 10,000 onwards, so that the numbers that were in the first connection can never be found in the second connection. So if I use the example that I've just given, that this first connection started at sequence number 1, ended at maybe sequence number 900 or maybe 2000, the second connection must start at a number far removed from that. So for example, it starts with sequence number 10,000. So now it will start with 10,000, 10,001, and so on, so that any number within the first connection, any number from 0 to 2000, can never, ever be found in the second connection. So that even if there was an obsolete data segment in the first connection, it can never be accepted in the second connection, because the numbers are just off. Okay? So that's also part of this three-way handshake. So remember, we have introduced sequence numbers. We have introduced this idea of three-way handshake. And then we have introduced this idea of the sequence number for every connection must be far removed from each other, so that there is no question of duplicates appearing in each connection. So let's relook at these problems that we have just looked at. Some of them, I believe we are going to look at some of them. So the normal operation of the three-way handshake is what we have there in A. So if A sends a request for connection with sequence number I, notice that B responds and say, look, my sequence number will be J. But I am acknowledging that you have sent me a sequence number I. So notice the acknowledgement there is I plus 1. So the acknowledgement is always what was sent by the client plus 1. And then the client, the server also gives its own sequence number, which in this case is J. Now, when the client responds, because now we are using the three-way handshake, when the client responds, it's trying to acknowledge the J. So notice what it does. It sends an acknowledgement for J plus 1, meaning I have understood that you want to create a connection, you are ready to create a connection, and you will start from J plus 1. But at the same time, the client also sends back its own sequence number, just so that they're in agreement. Just so that they're in agreement in terms of where will we start. So that is the normal operation for the three-way handshake. So let's revisit some of those problems we had. Remember the delayed SYN? So here we get an obsolete SYN that arrives. I don't know whether it arrives at a new connection or not, but an old SYN arrives. And in the two-way handshake, we said the receiver will not be able to detect that it's an obsolete SYN. So it just responds with its own SYN, so it would have responded with SYNJ. But in the three-way handshake, it must respond not only with its sequence number, but also the sequence number of the originator. So here it responds with sequence number J, but also acknowledges the originator's sequence number, which is I. So it acknowledges I plus 1. So now when the client receives this acknowledgement, based on the I plus 1, it can know whether or not this was a request that came from it. So assume it had sent an SYN-K and it receives an acknowledgement with SYN-I plus 1, then it will know definitely that was not what I sent. That is something else. And notice what the client sends. It does a reset. It says, look, this is not what I asked for. Let us reset and start afresh. So it's resetting itself. It's saying, look, me, that's not the number I sent you. That's really what it's trying to say. I did not send you I, but I acknowledge I have received your response with sequence number J. So when the server receives that message, it will know that something is wrong because the client is refuting. It's refuting having sent an SYN-I. It's saying, look, I did not send that. So if we go back to this diagram here, that one, that's really the one we are looking at. SYN-I arrives from a previous connection, and the server sends an SYN-J. But in this case, it would send SYN-J plus acknowledgement I plus 1. And when acknowledgement arrives at the server side, and the server has already sent K, it will refuse. Look, it will say, look, I did not send you SYN-I. I actually sent you SYN-K. So it will do a reset. It will refuse and it will do a reset, which means it will not enter the data transfer phase. It will refuse that connection. Okay, so I hope you have followed that. And maybe I forgot to mention the reset part, but there's a reset, there's a requirement for reset in this solution here. Notice that when a duplicate is detected, a control TPDU is sent to reset the other side. So in the three-way handshake, if there's any problem, you do a reset. Okay, so that's one of the problems. The second problem here is for a delayed SYN. Okay, so here you notice that the client side sends an SYN-I, so it initiates a connection, but there was a delayed acknowledgement from a previous connection. So, and here it's assuming it's already using a three-way handshake. So anyway, it sends an SYN-I and it's waiting for a response. But the response it receives is from a previous connection acceptance request that got delayed somewhere in the network. So it comes in and it is reading SYN-K and acknowledgement P. The acknowledgement should really be I plus 1 or acknowledgement I, but it's coming in with a totally different number P. So now when the client looks at it, it says, look, I sent you a connection request with sequence number I, not with sequence number P. And so it does a reset. Notice that the client there does a reset in diagram number C. It does a reset. But it acknowledges that the other side has sent a message with sequence number K. Now, when the connection was accepted, when the connection was accepted from the client side, from the server side, it actually sent an SYNJ and an acknowledgement of I+1. But now the acknowledgement comes in after a reset has been done. So now the client can do what we call the three-way handshake, and it actually says, okay, at least you have acknowledged that I sent you I, which means you can continue communication. So it acknowledges the J, and it also acknowledges that this connection, I'm starting from I+1. And then after that, the communication can continue. So what are we saying? We are basically saying that using the three-way handshake, you can overcome all those 4 problems we talked about. And for the ones we have not discussed here, please just go and try them again with the three-way handshake and see whether those problems will occur again. And ideally, they should not occur. If you're using a three-way handshake, the acknowledgement numbers will tell you whether you're having the correct connection, and you still also have the option to reset. And you have the option to start a new connection from a very far off removed number from the original. Okay, so you can look at those diagrams later. I think they're just a different way of looking at the three-way handshake. But what you're saying is that the three-way handshake allows you to create a connection even in an unreliable network. It allows you to create a connection correctly and to send data correctly without any of those problems. That's really what we are saying. So connection establishment on the internet is done using the three-way handshake, because the three-way handshake can take care of all the problems of lost messages, delayed messages, obsolete SYNs, all those things we talked about. The three-way handshake can take care of each and every one of those scenarios. And maybe what you should do after this, is go and try out each of those scenarios we talked about and ask yourself whether the three-way handshake can solve those problems. And please look in your, I think there's something there called past papers. I've sometimes brought this as a question in some of the past papers, asking you to show how the three-way handshake solves each of these problems, each one of them. How does the three-way handshake solve these problems, these ones? And you draw it using a diagram, just like we have shown in those diagrams. How does the three-way handshake solve the duplicate arrives after connection is established? How does the three-way handshake solve the problem of duplicate arrives after connection is closed? So one thing you need to do after today's class or this class, go and find out if you can answer that question. If you can't, please let me know. But let me see how far you have gone. So don't just come and say, oh, I don't know how to do it. Show me how you did it and how you got lost, or maybe something you didn't understand. But you need to be able to understand that three-way handshake is a solution to all these problems here. Good. I think we'll stop there and we'll continue from there at 2. And at 2, I think we will continue on to the connection termination.